like to think about it as a very good place to start writing more advanced quantum programs. One of the reasons why I wrote this book and this particular scope of topics. There are lots of books that talk about superposition and entanglement and measurement. But there is a gap in learning materials. How do you get from quantum computing 101 to solving realistic problems?
Want to be a quantum coder? There's no shortage of tutorials for your language of choice. But when you complete them, you might not feel ready to solve real-world problems. It's challenging to go from a scientific paper to practical code, and to do so with results that impress your boss. We've got a software engineer from Microsoft Quantum who's written a couple of books that should help you boost your skill set. Find out how to start your journey toward practical quantum programming in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is Principal Software Engineer at Microsoft Quantum and the author of 2 books on quantum coding. Mariia Mykhailova, welcome to the show.
Hi, thank you for inviting me.
Yeah. We both spoke at DEF CON Quantum Village. We didn't get a chance to hang out, so I figured I'd bring you here and hang out on the podcast. That's an extra benefit to doing this, get to talk to cool people. So you're an author, as I said, and you definitely follow the axiom of write what you know. So for the last 7 years, you've had a job at Microsoft that a lot of listeners would love to aspire to, something similar. So can you tell us about your day-to-day and what it's like being there?
My day-to-day can really vary depending on the time of year, what exactly I'm working on at this particular couple of months. I spent a fair amount of time with Microsoft Quantum working on education and outreach, a topic to which I naturally gravitated after the first release of Microsoft Quantum Development Kit back in 2017. It turned out that a lot of people are excited about quantum computing and excited to learn what it can do, but there was a certain lack of learning materials for this, especially learning materials that targeted classical software engineers, people with a lot of programming, software development experience, but not a lot of mathematical and physics background. So a lot of work I did targeted that audience. And at that point, my day-to-day would involve a lot of content development for the project, usually called the Quantum Katas, tutorials on quantum computing that focused on presenting the material through programming problems. So you would learn things by solving problems. And of course, implementing them. I'm a software engineer by training, so I really believe in implementing everything you solve. Then later, I spent a fair amount of time working on resource estimation of quantum algorithms. And that is a slightly different kind of thing, but some of the day-to-day looks similar. So there was some implementing quantum algorithms and then running them through resource estimator in our toolkit that allowed us to answer questions about those algorithms, such as how big a quantum computer, a fault-tolerant quantum computer, you are going to need to run this algorithm, and how long it will take to run this algorithm. Doing this kind of estimates allows us to figure out, for example, which of the 2 algorithms for the same problem is more efficient. Or is this quantum algorithm going to offer us a practical advantage over a classical counterpart or not?
That's really interesting. So are you at times then coming across resource estimation that says, we can't do this today? Are you hitting that? And then having to pick which one just won't run at all over which one will?
Oh, absolutely. The resource estimates we're doing assume that the algorithms are going to run at scaled quantum computers, quantum computers that are going to be fault tolerant, running error correction all the time to fix the errors that are happening. And this is not something quantum computers do right now. Over the past years, there were a lot of demonstrations of advances in quantum error correction, but we're still not at the point at which quantum computers run error correction continuously all the time.
Yeah. We just have those first logical qubits that have been appearing. And of course, Microsoft worked on that too with Quantinium and other things that are in the works. So do you then typically have to answer questions like which use cases might be the first ones that companies should be looking at, because we're right on the cusp, potentially within a couple of years, of them running and showing some kind of advantage? Do you have to deal with that?
Well, I wouldn't put specific timeframes on statements like this, but it is definitely interesting to see not even so much which algorithms are going to run first, but an interesting area to explore is which algorithms are not going to run fundamentally. For example, resource estimation is how we know that Grover search is not going to be practical, despite the theoretical quadratical advantage that it offers us. Once we get to actually implementing it for problems that look theoretically interesting, such as symmetric cryptography breaking.
Yeah.
Once we run it through the details of resources required to actually run it, it turns out that it's not going to pose a problem.
Yeah, even older papers on that topic thought you'd need around 6,500 logical qubits to even begin to weaken AES-256. That's a lot of logical qubits.
Yes,
so have we refined our understanding at all since then?
It's not just the number of logical qubits, but also the runtime. The runtimes are going to be quite astonishing. We're not going to have a single problem run for hundreds of years to get solved. Like if I want to run a solution in a quantum computer, my boss is going to start asking questions after a couple of weeks.
Yeah.
And well,
definitely not after centuries. They'll be interested in weeks for sure. Yeah. That's a really good point. So yeah, I want to dip out of that for a minute, and we're going to touch a little more on your thoughts about what's coming in the future. So you were talking about education, and you worked on the katas, and I love that name. I practice Bunjinkan, which is a type of ninjutsu, and so I definitely love the name and the approach. So would you recommend people learn Q# by starting with those?
The katas are a great place to start learning quantum computing overall. So they start with not even the basics of quantum computing, they start with prerequisites for it. Like if you don't know what complex numbers are or how linear algebra works, they're going to teach you that. And then they're going to walk you through the very basics of quantum computing, what is a qubit, what is a superposition, how measurements work, all the fun stuff. If you already know quantum computing but want to learn specifically Q#, the katas might be a bit of a beginner material for you. Also, it can be nice to go through simple problems just to learn a new programming language. I have certainly done that with classical programming languages. But if you want to learn more in-depth concepts of Q# and things like why certain design decisions were made in the language, my first book, Q# Pocket Guide, might be a good fit.
Yep.
I wrote it specifically not about quantum computing, but it's a language reference. So it walks you through all the language constructs in Q#.
Yeah, I was steering the conversation to that book now. Yeah. So the Q# Pocket Guide out from O'Reilly, that was your first book. And it's pretty clearly stated that you do need to have some of those prerequisites. So that's why I wanted to talk about the katas for a minute. Yeah, it's important for listeners to know. You should get a grasp of quantum computing and then dive into this. So you obviously work at Microsoft, so Q# is a natural fit. Can you tell us any of what you feel are the benefits of Q# as a language?
My single favorite thing in Q# is the ability to allocate qubits temporarily mid-circuit and then deallocate them. So I run into it all the time whenever I write any kind of reversible computation, for example, because they rely on auxiliary qubits so much. It is just so convenient. Like if I want to add two numbers, I don't want to keep track of how many auxiliary qubits this is going to need. And if I want to change the implementation a little bit, I don't want to change the code that calls all the additions. So this is the single thing that is my favorite. Not even going to think about anything else.
Wow. Okay. So that's pretty cool. That's a very concrete answer, something that people can measure in terms of like how it changes their life when they do it. That's great. Yeah. That makes a lot of sense. And that said, your forthcoming book, it's going to cover Q# and Qiskit, right?
Yes.
Yes. And that's going to be called Quantum Programming in Depth. So it's not finished, but it's sort of available. So Manning Publications does a serial kind of publication. It's sort of like your Charles Dickens in a technical world, giving us a little bit at a time. Can you tell us how early access works on a book like that? And then we could talk a little bit about the book.
Yes, absolutely. So early access is based on the idea that books take time to write. This book I've been writing for 15 months now. Well, that happens when you do it in your spare time in parallel with doing your day job and teaching and all the fun things. Books take time. But at the same time, this is kind of cutting-edge technology that you want to start learning as early as possible. So early access does exactly that. The chapters that are already written and went through some reviews and edits are made available online even before the book is finished. And then once the book is complete and has gone through all the edits and all the Z articles are in place, those are my personal nemesis. Then the book gets published in paper, and folks who were reading it online in early access get shipped their lovely paper copy.
And there could be changes at that point, right? Things that have been adapted or updates because of how time has passed or anything.
Yes, of course. I have already reworked the first chapter between the first time I wrote it and the time it went to early access. And I fully expect to rework it again in a couple months, just to reflect the latest progress in the state of quantum computing.
Yeah, and your publisher was kind enough to give us a link to put in the show notes so people can take part of this. And what's great about that is, like, you sometimes hear about books now, and it's like, do books even make sense anymore in the technical world? Everything changes so fast, et cetera. Programs like this show you that there's a way to still have that and keep it relevant and up to date. And I think that's great. So that's a good approach. And one other point I wanted to note in looking through the chapters is you can tell that your day job is heavily involved in helping people learn this stuff. And they obviously give you feedback in real time in that process. And that's been sort of guiding you in the way that you approach the teaching methodology. So if anyone's ever been kind of like intimidated by a quantum book, you could see it, that Mariia does this kind of daily. And that's sort of like top of mind, how to get across these concepts. So I had to say that one great thing about it for sure. Is this designed then ultimately, when all the chapters manifest, to be more of an all-in-one guide? It sounds like you don't need to go anywhere else, really. Like, you will be taken through and actually able to start programming rather than worrying about scrambling to different sites.
I like to think about it as a very good place to start with quantum programming, and especially to start with writing more advanced quantum programs than random number generator. Mm-hmm. One of the reasons why I wrote this book and this particular scope of topics, there are a lot of materials that introduce the basics. There are lots and lots and lots of books that talk about superposition and entanglement and measurement. But there is a gap in learning materials. How do you get from quantum computing 101, like random number generator and teleportation, to solving realistic problems, to, for example, just taking a paper and implementing it? Mm-hmm. This is a pretty big jump, and it takes both a certain level of practice with quantum computing itself, with solving problems in it, and with actually implementing more complicated algorithms. So this gap is what I'm trying to bridge. So the person who reads the book, they're not going to become a quantum chemistry expert, for example. But I really hope that they are going to become a quantum programmer who is going to have a much, much easier time once they learn quantum chemistry, bringing those learnings into actually runnable code, or the code that we can run through resource estimation.
That's a great point. That being able to implement a paper is the key skill, right? Ultimately, in the real world, when we're building use cases, there'll be people who run like sample code or whatever. They'll go to a tutorial like for QizKit or something, and then that doesn't prepare them in any way, shape, or form for going into a customer and saying, "Oh, which problem do you want to solve? Yeah, there's a great paper that just came out on that," and then they can't actually connect the dots. So that's fantastic. So that's like probably one of the biggest selling points for an approach like this, and that'll probably impress your employer too. I mean, whoever you are listening to this, if you wanted to try and actually accomplish some of this, will it get into anything like tweaking performance based on platform?
I am going to talk in the last chapter, the one that's not published yet, about how we think about performance of quantum algorithms. Because sometimes I see people think about performance of quantum algorithms based on things like the time it takes to run a small instance on a simulator. But this is not representative in any way of how much time it will take an actual program to run at scale on an actual quantum computer, because there are so many factors that impact this runtime. So I spent a whole chapter talking about how we think about that performance. What are the things that impact it? What are the considerations we need to take into account when we are comparing a quantum algorithm with a classical counterpart? So all these kind of more advanced topics, then again, topics that are not 101, topics that you need to understand to get to the next step. But I'm not going to talk about specific performance tweaks depending on the platform. That I leave as an exercise to the reader.
And I have to ask, because you're from Microsoft, how does Copilot, how has it impacted what you do daily, both in writing code and helping people learn? How does that tool start to like change quantum coding?
Right now, I would say Quantum Copilot is a great tool for looking things up, but it's not great quite yet for writing actual quantum code. Now, among the many, many things I do on a daily basis is teaching a class. And when I teach, I have to grade my students. I have to give them those final grades. And I do it using programming assignments that are automatically graded, because I don't really want to read any kind of essays that my students would write. And it's a quantum programming course. Essays are out of scope. So I have assignments that are graded automatically. So for example, the goal is to prepare a specific state, and then the test checks whether this state has indeed been prepared, regardless of which path exactly the solution took to do it. So, of course, one of my first thoughts is Copilot going to mess with it? Are my students going to be able to pass those assignments without putting in any thought, just the copy-paste skills? Well, the good thing is right now they cannot, because Copilot is, at this point, a large language model, emphasis on language. So if I ask it to write some C# code, it will. And it will be very beautiful code, well formatted, well commented. But since it's a language model, it's not going to be able to do the math required to solve quantum problems that you then implement in code without some special tools. So it is certainly possible to augment it with tools that are going to, for example, take a quantum state and then mathematically parse it and decompose it into a sequence of gates that is going to do it, and then convert that sequence into code. Right now, it doesn't do that. So the code it writes is going to be very beautiful, but it's not going to prepare the state you have in mind. It's going to prepare some other state, most likely.
So for it to advance, you're imagining something like a Wolfram approach where LLM has to reach out to tools to actually get things done correctly. Like he always pointed out that it would be terrible at math, so why not just teach it to go use a math tool of some type, right?
Yes, and I mean, it makes sense. Computers are really good at math as long as they don't approach this as a language problem. So it does make a lot of sense to have specialized tools similar to retrieval augmented generation, in which it doesn't try to come up with something, but rather it focuses on looking up something before it generates the answer.
Absolutely. Yep. So how far are we, you think, from some system being developed, some kind of mixture of agents or whatever it might be that allows Copilot or some future version to get you a little closer like that, to maybe make half a developer's job easy and then the other half advances, something that you could like tweak per case? You know, like let's say someone wants to do a use case in, I don't know, fraud detection or something. How long do you think before Copilot can then at least get the rudimentary basics down and then you sort of adjust it?
Oh, you know what they say, prediction is hard, especially about the future.
Yeah.
So I think this depends largely on which areas of Copilot development are prioritized. For example, right now, Microsoft Quantum specifically, is working on some new and interesting generative AI workflows, but they focus on science applications. So things like generative chemistry, things like generating materials with given properties. And this is a very interesting problem with really interesting implications of what we can generate using such approaches and how we can speed up inventing new materials. But it's not specifically quantum. It focuses on properties of materials rather than on quantum code. So, and basically, if the team is working on this, the team is not working on Copilot for quantum code. But ultimately, this is a very interesting problem to look into. I know a lot of companies already started looking into it, and I'm really looking forward to what they come up with.
Yeah, I mean, none of us want machines to replace us anyway, so it would be good if it can help people get a little closer along the way. So on the topic of use cases, we're expecting about 100 logical qubits within maybe 2 or 3 years. Multiple vendors are kind of guessing at that being their roadmap. And that's obviously out of the realm of anything we've been able to simulate fully without any kind of tricks or, other sampling and things like that. So what kind of use cases do you think will be promising first once we hit that unknown frontier based on resource estimation and experiments you've done in the past?
At this scale, we expect it's going to be computations that help us understand certain scientific problems and chemistry problems. So material science, quantum dynamics simulations, those kinds of things.
So yeah, a more controlled environment than something that's running in production 24/7 to churn data in a company to make the money, maybe.
Yeah, something much more scientific, something much more supercomputer-like.
Shifting back a little bit to what you do with education, if you were going to advise someone young on the path to having a job in quantum development, maybe similar to yours, maybe in a private like company that just focuses on one task, what action steps would you provide in addition to reading your new book, which of course sounds like a really great start?
So I would advise to start by making sure that you have a really solid background in math fundamentals and then software development fundamentals. So very often I see people who come to interviews and they struggle with the basics, with again things like how do you prepare like this given state? How do you check that the state that you prepared is the state you actually wanted to prepare? Those are the very fundamental things, and I see a lot of people struggle with it. Even so, they spend a lot of time learning quantum computing, taking courses, going through tutorials. So a solid foundation in software engineering, but also in math, is extremely important. I learned everything I know about quantum computing on the job. I came in as a fully formed software engineer, and then I learned only the quantum computing parts for it. And a lot of people I work with come from a similar background. They come from software engineering background, from a lot of experience working with compilers, for example. And then they bring that expertise into the quantum computing world.
That's great. I'm sure a lot of people find that inspirational because they might have already started on the path and they're deciding, no, I want to look into quantum. So that's helpful. And that said, if they've already started the path and they're in college, how do you feel about the current state of like higher education with quantum? I still personally see it as very, like they don't have these clear-cut majors that you can get away with actually working after, right? Like I don't see too many bachelor's degree in quantum coding, like that just doesn't seem to pop up, or an emphasis in the area. How do you feel that can change and be done better right now?
I think there are indeed not a lot of bachelor's degrees. I have seen quite a few master's degrees in quantum computing, and of course, plenty of PhD programs. The course I teach myself is for software engineers and more broadly engineers who are not going to specialize in quantum computing specifically, so it's more of an overview course. So I would say it's really important to focus on those basics and then see which area you are most interested in applying them to. Because one thing we have to be realistic about, we all love quantum computing, but it is a very small area in terms of the number of jobs compared to classical software development. So it can be challenging to get a job in, based on the sheer number of jobs worldwide in it. So for the purposes of making sure you have a job, I would say it makes a lot of sense for young people to focus on bachelors in more basic, more fundamental areas from which you can branch into any number of directions. Quantum computing, but also AI, also some other sort of science, also really whatever branch of classical computing exists out there. Then to focus the fundamental learnings on quantum computing specifically. I just like to have this flexibility for myself, and I also like to have it for my students, or at least for people I give advice to.
And so to clarify before I let you go, you mentioned a few times about like on the job, learning things on the job and everything. Does Microsoft have a system in place for elevating quantum skills? Sort of like a dojo to go along with the katas?
When I joined the team, it was the first time Microsoft Quantum hired software engineers without quantum computing backgrounds. So there were a few of us joining at the same time to work on the first version of Quantum Development Kit. So the team put together a whole bootcamp for us. So we got, of course, the Nielsen and Chuang book, but we also got a number of lectures from the researchers on the team on different areas. And then we had a longer lecture series with more deep dive into some algorithms and more exercises. But this was before quantum programming languages, before C#. So all the exercises were pen and paper. That's how I figured out I want to do something like the katas, but with programming. Because if I do an exercise in pen and paper, I need to get somebody to review it, to say, is this correct or not? And I had plenty of access to quantum computing experts to do that. But a lot of people who learn just don't get that access. And for them, this getting the feedback on their work immediately is really important to maintain their studies, to support them.
Yeah, I would think the larger the team is, the bigger the company is, it's easier to implement something like a apprenticeship or some kind of shadowing in place, if you're not small and crunched for generating a profit or something where like you have two people and they've got to be working, 80 hours a minute somehow. That would make sense. So thank you. I think a lot of people are going to find this really interesting that want to try and advance in this type of career. And like I said, there's this book currently in progress. You can read it as the magic happens and go along those important lines, including how to actually translate something like a paper into code that will run. So I really appreciate you writing that book and coming on here to talk to us about it.
Thank you for inviting me here. I love writing this book, and turns out I love talking about it.
Great. That works out for me too then. Thanks. Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Mariia joined the Microsoft Quantum team in 2017 with no experience in quantum coding. Of course, back then, almost no one had much experience in quantum coding. She worked with the team to develop the first version of the Quantum Development Kit, and then coding boot camps and the quantum katas to help developers become quantum coders. She knows what it takes to go on this journey, which shows in her writing. The quantum katas are a great online resource to learn some of the prerequisites for quantum programming, and Mariia augmented them with her first book, Q# Pocket Guide, where readers could experiment with her favorite language hands-on. Mariia's new book, Quantum Programming in Depth, will provide a complete guide to becoming a practical programmer. Employers want someone who can go from scientific paper to usable code and do so with performance in mind. This book aims to provide that path. However, developers should still acquire solid foundations in math and software engineering for the best results. Mariia explains that Q# is a great language because it allows you to temporarily allocate qubits mid-circuit and then deallocate them. This makes future code changes a lot simpler. When learning the Q# language, Copilot will help you look up these and other features of the language, but the LLM is not ready to replace human coders anytime soon. There's still plenty of time to get on the path towards a new career without worrying about AI obsolescence. Check out the show notes for a link to the new book. That does it for this episode. Thanks to Mariia Mykhailova for joining to discuss the journey to practical quantum programming. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.